All right, so welcome back for three, part three of section 3.7, related rates. We're going back to that problem we started the beginning of the section with. We got a cone full of water. A water tank has the shape of an inverted circular cone with a base radius 2 meters and a height of 4 meters. If water is being pumped into the tank at a rate of 2 cubic meters per second, find the rate at which the water level is rising when the water is 3 meters deep. And in case you didn't know, the volume of a cone is V equals 1/3 pi r squared h. Okay, so yeah, okay. I think I'm okay with this. They told me this: V equals 1/3 pi r squared h. I'm supposed to find the rate at which the water level is rising. So that would be dHdt. And when am I supposed to find this? When the water is 3 meters deep. So when h is equal to 3. All right. So I'm going to go ahead and differentiate with respect to time. d dt. Okay. Starting from the left, derivative of v with respect to t. Well, implicit differentiation says that will be dv dt. Moving to the right, pi over 3, the 1/3 pi over 3 is a coefficient, which is going to get multiplied by everything. But I've got an r squared times h in there, so that's going to be a product rule. So the derivative of r squared is going to be 2r times dr dt times h plus r squared times dh dt. I'm going to make that parentheses a little nicer. Okay? And so now I'm looking at this and I'm seeing 1, 2, 3, 4, 5, 6. I mean, the r is the same in both places, so maybe only 5 variables. Okay, but we're going to have to put a value in for that. And what does they want me to solve? Okay, they want me to solve for this one, dH dt. So that means that the rest of them must be given. Okay, all right, so what's dV dt? dV dt is the rate of change of the volume with respect to time. Now, this sentence right here tells me that the water is being pumped into the tank at a rate of 2 cubic meters per second. 2 meters cubed per second. And is that going to stay a positive or will that become a negative? Well, if the water is going into the tank, the volume is increasing. If the volume is increasing, the derivative needs to be positive. Okay. I know h is 3. 3 what? Feet? Meters. Meters. Sorry, meters. We're going to put a metric. But there's a whole bunch of r stuff in here and dr dt, and there's no r or dr dt given anywhere. I mean, they tell me the base radius, that is the top of this cone, is fixed at 2, but that's not the radius of the water, because the radius of the water is changing. That's why there's a dr dt also. All right, I've got a problem. They're asking me to solve for something, and I have insufficient evidence. So this is kind of like the ladder problem where they gave us x, but they didn't give us y. And so we're going to have to find a way to go back into here and figure this thing out. We're going to have to find a way to find a value for r as well as dr dt. So how can we do this? Okay, I'm seeing it. I'm hoping you're seeing it too. Do you see the similar triangles? Do you see the similar triangles? Of 4 and 2 and r and h. This angle is the same for both of them. They're both right angles, which means that that third angle must also be the same. And since that third angle is the same, then we're looking at similar triangles. And if I have similar triangles, I can set up ratios. I can say that r is to h as 2 is to 4, or What's that going to give me? 2R is equal to H. You know what this tells me I can do? I can take this information and do a substitution way back up there in the orange and then never have this hot mess of a derivative. I can do that substitution and say, well, R is just equal to H divided by 2. Rewrite the original problem as volume equals pi over 3 times H over 2 R squared times H, which gives me pi over 12 H cubed. And then when I ddt, I get dv dt is going to be equal to pi over 12, the coefficient, times 3h squared times dh dt, and I've gotten rid of that offensive r in dr dt. So I simplified the problem down. Now, that does not mean that what I did over here in the orange and the blue is wrong. I took what was given to me, which made sense. I took the derivative because that's how I've been doing all these problems. But I ran into an issue, right? And this is how we make sense of math. When I get to a new problem that looks like an old problem, I do it the same way. And if everything works, then that was the right way to do it. But if something doesn't work, then maybe I didn't do it the right way and I have to rethink it. Right? So I ran into an issue when I took the derivative like I did in every other problem. I ended up with variables that I don't have information for, and I don't have any way to figure out the information for those easily. So I need to rethink things. Right? Maybe that variable can't be in the equation. And how do we get rid of variables in equations? Well, the only way to get rid of a variable in an equation is to do substitution. And so we substitute out. And when we substitute out, things go away. When things go away, life is good. Right? So now I can come down here and I can put in the values for the things that I know. I know that the volume is increasing at a rate of 2 cubic meters per second. I know that the height is 3 meters, and I know that I'm supposed to solve for dH dt. Okay? So plugging in everything where it goes, I get 2 cubic meters per second is equal to, let's see, that pi over 12 is going to turn into what? Pi over 4 times 3 meters squared times dH dt. I'm going to drag this up over here so I can keep the space down at the bottom for writing the final answer. So then I get, let's see, this junk is being multiplied by dH dt. So that means that dH dt is going to be equal to 2 cubic meters per second divided by, let's see, 3 meters squared is 9 square meters. 9 pi over 4 square meters. So then dH dt is equal to 2 times 4 over 9 pi. Meters cubed per second divided by meters squared is meters per second. That's 8, right? And so then dH dt is 8 over 9 pi meters per second. Right? Or, wrapping it up, making it look pretty, writing it as a sentence, the height of the water is increasing at a rate of 8 divided by 9 pi meters per second. Now, if you really want to be really specific, you could say at 8 meters per second when the height is 3 meters and water's being pumped into the tank at 2 cubic meters per second. We don't have to necessarily be that specific every single time. Okay? All right. Last example. A man walks along a straight path at a speed of 4 feet per second. A searchlight is located on the ground 20 feet from the path and is kept focused on the man. At what rate is the searchlight rotating when the man is 15 feet from the point on the path closest to the searchlight? And this is the drawing from the book. It attempts to capture it, but the perspective is a little bit off because it's trying to show three-dimensionality. Okay, so if you were to draw this one, just top-down view, this is the light right here. This is the man. The man is walking in this direction. Okay? This is the distance x as it's labeled in the drawing. This is 20. This is a right angle. So this is the spot on the wall that is closest to the light because it's at a perpendicular to the light. And then this angle theta right here is changing because as the man walks, this angle needs to rotate, or that light needs to rotate, so that angle needs to get larger and larger and larger to keep up with keep the spotlight on the man as he's walking. Right? I know that the man is walking at a rate of 4 feet per second. Okay? So that tells me that the x is changing. That is dx dt is equal to 4 feet per second. I also know that this is when x is equal to 15. That is when he's 15 feet away from the point on the wall where it's closest to it. And my job then is to solve for d theta dt. That is the rate of change of the angle with respect to time. Okay, so I need to come up with some sort of an equation because this problem doesn't give me one. I need an equation that's going to relate a right triangle, an angle in that right triangle, a side opposite that angle, and an adjacent side. So what trigonometric function do we know that deals with an angle, the opposite, and the adjacent? Tangent. The tangent of angle theta is equal to the opposite x divided by the adjacent 20. And x and theta are both changing with respect to time, so we can differentiate, that is dt this thing. So tangent is secant squared, so left-hand side becomes secant squared theta times d theta dt, chain rule with implicit differentiation in there. Right-hand side, 1/20th times dx dt. Okay? My job is to solve for this. So that means that this must be given, and dx dt was given. It was 4 feet per second. And theta must be given. But theta isn't given. So what do I do? Last time I had a right triangle problem and I wasn't given a piece of information that I needed, I solved for it. So maybe that's what I need to do here. Maybe I need to go back to the green and solve for theta and say that tangent theta is 15/20, which is what, 3/4? So that means that theta is the tangent inverse. That's it, arctangent of 3/4. So then taking this and putting it there, I should be able to solve this thing. So the secant of the arctangent of 3/4 squared times our d theta dt is going to be equal to 1/5 feet per second. Remember, this is theta right here. So there's the secant of theta squared. Right? My job is to solve for d theta dt, so I'm going to go ahead and solve for d theta dt. I get then that d theta dt is equal to 1/5 feet per second divided by the secant of the arctangent of 3/4 squared. Yeah? No, I didn't know the parentheses in there. Yeah, there we go. And I'm going to tell you that that's nothing I can do by hand. That's a calculator problem. So the first thing I'm going to do is I'm going to find the secant of the arctangent. So arctangent of 0.75, 3/4, gives me some number. And then I'm going to do 1 divided by the secant is 1 over cosine, right? 1 over cosine of that number. And then I'm going to square that number. And then I'm going to take 1/5, 0.2, and divide it by that number. And I get 0.128, exactly 0.128. There is a trigonometric way to find this by drawing triangles and all that. You could set that up, right? But I'm not too worried about it, right? But what are the units on this? Well, what are the units on theta? What are the units on d theta dt? Radians per second? So this is going to be radians per second. So when the man is 15 feet away from the closest point, that angle is changing at a rate of 0.128. If you prefer as a fraction, that is 16/125 radians per second. It is the rate of change of the angle. So the angle is increasing at 16/125 radians per second. All right, that brings us to the end of section 3.7, related rates. Next section is 3.8. I believe section 3.8 is the last section in this unit, so we will have an exam also this week. All right, see you back here for section 3.8.